Hey guys, welcome to another episode of CUDA Education. We are continuing on our journey of Frustrum culling and level of detail stuff, right? So for you guys that are new to the project or this channel, basically we have an application here that deals with it shows an object and their level of details associated with the object. So closer objects have high levels of detail, and as we zoom in, I'm gonna freeze the frustum for a while. As we zoom in, based on our initial world space view, we get less and less detail, right? And that makes sense because we are trying to save processing power and save energy, save system resources. We don't want to be calculating stuff that we don't need to. So obviously the things that are way back here, we don't have to, the mesh for creating the object, we don't have to put as much intricacy into it because alas, it is farther away. So when I don't freeze the frustum and I zoom in, you could see that all these objects eventually turn green because they're closer to me, right? And notice that like the red disappears and everything eventually turns green. And then, you know, we're zoomed all the way in, okay? When we say freeze frustum, we're talking about freezing the initial view of the camera. So right now there's an initial view of the camera. If I freeze it, only those objects that are in the initial view stay. Everything else is called out. Everything else is removed. Everything else is discarded. And we know that because once I move the camera now, things are discarded, okay? So notice that things are discarded, right? Now, if I unfreeze, we get back our objects, right? Because now we're not culling based on a specific perspective or a specific view. If I refreeze, these objects will be viewed, but alas, all these objects are gone and all these objects are gone, right? And this is thing, right? So my initial thing, if I unfreeze, I get back. So there you go. That's what the frustum is about. Now, there is an equation associated with this process. And what we do is in the cull.comp or cull.comp shader. Now remember, shaders are GPU side, and we're culling based on the GPU, using a GPU process, right? Because it's a shader in here. We have this function called frustum check. And really, we have our main function here, and we have this frustum check that is basically called, and if the check passes, we display the object. If the check doesn't pass, we don't display the object, right? Which we just visually saw. Let's deep dive into this frustum check function, which is right here, okay? the heart and soul of this is the dot product of the position and the frustum planes plus the radius is less than 0, right? So this is the heart and soul. If this passes, then we do not display the object. If this equation fails, then we display the object, okay? So, before we deep dive into this particular piece, notice that we're testing it against 6 planes, right? So notice that you have this frustum planes, okay? And the reason for that is because if we go to this video, I will link it in the description below, educational use, fair use. But notice that we have our camera here, and then we have our frustum, right? So this is the view space of the camera, okay? So if you look, we have the top view, side view. So 1, 2, top view, side view, bottom view, side view, front view, and then there would also be a back view here, which we'll see in a second. So we have 1, 2, 3, 4, 5 for the front and 6 for the back. So we have 6 planes. And as we go further, we could kind of see all the 6 planes here, right? So I know the perspective is awkward, but we have all our side and stuff. We have the front view and the back view, right? So yeah, it's kind of awkward to see, but basically, like we did in the application, now we're doing it here. I will link in the description below, fair use, educational use. But all of these boxes, green boxes, right? And as the camera moves, things get discarded and things get included, right? So that's basically what we just did in our application. Now, a very important thing that I want to also mention, and we'll get into it in a second, is that obviously these two objects are within the view space. This object is also considered within the view space because a piece of the object is within the view space. So if a piece of the object is in the view space, we display the whole object, right? This counts as within the view space, okay? And we'll get into that discussion in a minute. All right? But when we get back to this this equation, this test, but you understand now why there's 6 planes, the 6 planes that are tested. So we test against all 6. Notice that we do a for loop of 6 things, right? And notice that the I that we're looping over is basically we're changing the plane. So we're testing over all of these 6 planes, and we're making sure that, you know, if it's less than 0, then the check is false. But if it's greater than 0, then we show the object, right? So let's kind of go a little bit deeper into this test right here. Also pay attention to the fact that we have this dot product here, but then we also have this plus radius, which is very important, okay? So in our application, we're actually doing, we're using spheres, right? So imagine when we run our application that each one of these objects, we're not testing for, you know, the curvature necessarily, the intricate curvature of the object itself. We're putting an imaginary sphere around the object, and then we're testing whether that sphere is within the world space. So I know this is obviously not a sphere, but we put an imaginary sphere around it in order to you know, process and figure out whether the object is within world space. This is along the lines of axis aligned bounding boxes, AABBs. I have done videos on this specific topic before, especially as it relates to ray tracing, right? But we're putting spheres around stuff, and then we're saying we're doing a test to see whether that sphere falls within our view space, within our line of sight, okay? So going back to this equation and also the plus radius, if we go to this guy, fair use educational purposes, I will link the video down below. You will see that basically we talk about the same idea, view frustrum, and we have our plane and we have our object, right? This, we're going to say this side of the object is in view space, and this side, this side of the plane is within view space, this side of the plane is outside of the view space, right? And we do a bunch of mathematical stuff, which you could watch this video to get a better understanding. We have our normal, we have our distance to, 0, 0 coordinate, all of that stuff. But, I'm not going to get too much into it, but basically, we basically have our, we basically get our equation that we, or somewhat of our equation that we want, right? But we're basically testing to see whether the distance to the object from the plane is within our view space, okay? And, this video will get you a little bit a deeper dive into it. Now, the nuance and the complication comes into the fact that we have, not only are we doing the dot product of the position and the plane and all of that stuff, the dot of this, but we have this plus radius, okay? And why do we need this plus radius? The reason we need this plus radius is exactly because of this problem right here. So this is inside of our frustrum on the right side, the correct side of the plane. This is outside of the plane, okay? The problem comes in when we have an object that, remember, we're putting spheres around these objects, right? So we're putting spheres around each of these objects, right? But we don't just want to test for whether the center of the sphere, so let's say an imaginary sphere is around this object. We're not just testing for whether the center of the sphere is within view space. We also have to test whether, a piece of the object is within view space. So, let's say let's say this guy, right? So this object right here. Notice that only a piece of the object is within view space. It is still valid, right? We still have to show this object because we don't want to prematurely discard this object because it's still within our view space, but only a piece of it is. In order to deal with that problem, we go to this, part of this thing where we have to add in, it's not just whether the center is within the view space, right? Not just the dot, but also even if a piece of the sphere, even if just a little piece of the sphere is within the view space. So that's what this plus r radius is. The plus radius is also trying to take into account whether just a little piece. So notice that it's not just the dot, because literally if you're only testing for the center of the sphere, this object would be considered outside of our view space, outside of the frustrum, outside of our world view line of sight, right? But because we also include the radius of it, we have to include a little piece of the thing, which is similar to this, right? A little piece of the sphere, a little piece of the object, right? And it would be wrong for us to prematurely discard this object because a little piece of it, because only a little piece of it was showing. It would be an incorrect rendition of what's actually happening in the world. I mean, you know, this is what, like, especially action video games and stuff is made of, right? If you don't want to, be shot down or something by an enemy force that you didn't even know was there because you couldn't see the piece of the object, right? So that's what this radius is trying to capture. So I don't want to get into too much of the math. I would definitely recommend you guys on YouTube just type in Frustrum Culling and see, especially Frustrum Culling math, and see all the videos that come up as it relates to understanding the equation that is used to test for whether an object is within view space or not. Now, before I end this video, I do want to play around with this a little bit. Okay, so let us just all right, so we'll just run our application, right? Just normally, right? So when I expand the window and everything, I don't zoom in, I don't do anything, I don't touch anything, I just leave everything as is, right? But the window is expanded. When I change the size of the window, this number changes, okay? I'm not freezing the frustum or anything, right? Notice that we have visible objects of 32,000 plus, okay? Fine, right? This is including now the radius, right? So we're including not just the center of the sphere, but also, you know, the halo, the full radius of the circle, right? Okay. Let us take out the radius portion of it, right? And I actually have to compile my shader. So I compile the shader and we're gonna now run the application again, okay? So I run the application again, I expand the window. Notice that the number of visible objects has declined. I don't fully understand why it's declined or what's necessarily going on, but I believe there's like a boundary that's set for all objects in the application, and if we don't include that space, if we don't include the radius, then objects fall out of the boundary because now they're prematurely discarded, right? So now we're at 27,000. Okay. I'm gonna go one step further. So let's put back in our radius. I have to compile my shader. Let's run the object. So we're back to normal now. All right, we're back to normal. We're at the 32,000 plus. Fine. I'm not touching anything. I'm not freezing anything. I'm just leaving things as the way they are. All right. Notice how the breakdown of the objects are. Okay. So we're at 32,000 for visible objects. And then the level 5 is it level 5 or level 0? That wouldn't even make sense. But anyway, so we have 22,860 for level 5, which is let me see something. Okay, so level 0 is the detailed. Okay, so let's just run again. Okay, so all right, we're at 32,000 and 22,860 for level 5. Level 5 is the furthest out. All right, the furthest out. All right, so we're at 32,000 for total number of objects, and we have 22,860 for the furthest out objects. Right? Okay. That's with the radius. Watch what happens now when we take back out the radius. You guys know I gotta compile, and then we're gonna run our application again. Now 27,000, 19,930. 27,000, 19,930. So the majority of the deficit, I think, was taken out of level 5, right? I did this before, but what was this? 19,000, 19,000. So let's call it 20,000, right? So 20,000 here for level 5, right? Let me just put back in. So 22,860, almost 23,000, right? So notice that the level 5 stuff, actually, you know what? Yeah, so 22,860, but notice that a lot of the deficit, 22,860, so like, yeah, a good almost, majority of a good portion of it is from the outer items, right? So I gotta compile shader. So a good portion of it is from the level 5, which I believe is the outer bounds and what have you, right? So this test is very important, right? And again, notice that we have to test against the 6 planes. Okay, so this is a very important concept. Also look at other videos related to this. But this test is very important, okay? Let us not call anything at all. So I'm going to disable now the Frustrum check, okay? So when we run it, I gotta compile. So when we run it now, notice that we get 262,000 plus objects, right? Because basically now we're not calling anything. Like everything is being shown, right? It's just when I enable, culling, we get to more reasonable things that we know from before, okay? Let us call everything. So no matter what happens, the Frustrum check is going to return false, right? So everything is going to be discarded. What do you guys expect to happen? I have to compile my shader. What do you guys expect to happen if we make everything false? We get a blank screen. 0 visible objects. LOD 0 is 0. LOD 1 is 0. LOD 2 is 0. LOD 3 is 0. LOD 4 is 0. LOD 5 is 0. That makes sense because we have basically called everything. The Frustrum check always fails, right? But we're not going to do that. All right, so that's kind of the lesson for today. I'll have to deep dive more. Check if the object is within current viewing Frustrum. So we do a check. either we do indirect draw instance count 1 if it passes, and then we do indirect call instance count 0 if it isn't, which means that, you know, we discard, right? Let me just show that we're back to normal. Oh, I have to recompile. Okay, let's just show that we're back to normal. So we're back to normal again, right? Let us from the main loop, we're gonna just discard everything. So we're also, even if the frustrum check passes, we're gonna discard. We're still gonna discard. We're not gonna draw. We're not gonna draw. I have to compile my shader. So even though the frustrum check passes, we're just not gonna draw. And if we don't draw, we don't get anything, right? Which makes sense. This is disabling everything on the draw side. So apparently this indirect draw thing is a draw being issued from the GPU side, right? So that's one of the purposes and demonstrations of this application, is that we could issue draw calls from the GPU itself. So traditionally, draw calls are issued from the CPU. So this is a shader. Cull.comp is a shader. This is, you know, our source code, right? CPU side. So normally draw calls are issued from the CPU and then the GPU does stuff. But here with this indirect draws bit, which I'll have to dive in later on because I just, yeah. Apparently this draw call is being done from the GPU side. It's being done within the shader. So, guys, you guys should know by now that we have our compute cull and LOD application. We have the source code, which is this guy, but then we have our shaders, which is our cull.com. So we have indirect draw frag and indirect draw vert, right? So these are the cull, and the indirect draws is our shaders on the GPU, and then we have our source file, which is CPU side. But these draw calls are on the GPU side, which is a big demonstration point. I don't, you know, as I say, in my personal current development, you know, I can't fully appreciate it right now, but it's actually a big deal. The fact that you could issue draw calls from the GPU side, right? So that is what this application is actually, also trying to show, right? So we kind of have a better understanding when it says compute shader culling, right? Because we're culling based on mathematics, and we're doing, so compute shader culling. So we're culling, we're removing stuff, we're culling based on mathematics, right? Because we're doing this test right here, right? So we're culling, we're removing stuff, we're computing because we're culling based on mathematical stuff, and then it's shader because it's on the GPU side, right? Shaders live on the GPU, right? And then level of detail because when we run our application, let's say we freeze the frustrum, right? So we're freezing everything as is, and then we zoom in, level of detail declines because the further away the objects are, the less intricate the mesh has to be. And of course, you guys know the more intricate the mesh is, the more processing power and all of that stuff, right? So if I unfreeze now, the green objects stay with me as I zoom in, and the red disappears because now we're closer to the objects, right? So that's the level of detail. So we have a better understanding. So compute shader culling and LOD using indirect rendering. Indirect rendering, we're talking about indirect draws, right? So we're drawing from the GPU, right? We could also draw everything regardless of whether the frustrum fails or not. We could draw everything. I have to compile my shader. We could draw everything, and I suspect we'll get our same result that we got before. We got, no, hold on. Maybe not. No, it didn't work. I don't know what's going on there, but did I forget to do something? I did compile. I don't know. But anyway, so right. So we have our we now understand what this is saying. Compute shader, culling, and level of detail using indirect rendering. We actually have some insight into this, guys. Aren't you proud of CUDA education? What a way of saying it. I mean, I understand, for someone that is well versed in computer graphics will say this, but for everyone else, it's a little bit involved, right? So that's pretty much it. The only thing I have to worry about is I got to make sure that I put everything back to the way it was. So we draw if the frustrum checks out, and we don't draw otherwise. We have our radius in. If this is true, we exclude it. Otherwise, we return false. Otherwise, we return true. We check the 6 planes. Actually, that's a good. Do I want to do it in this video? All right, let's just mess around. We're only gonna check 2 planes, right? So let's see what happens if we just check 2 planes. All right, so we get 75,000 objects if we check 2 planes. What happens if we check more planes? Is the number going to go up, or is it going to go down? If we check more planes, the number should go down, right? The number should go down, right? What was 2? 2 was 75, right? But I didn't maximize the window, or did I? Yeah, it was about 76,800 when I maximized the window. And then when I check more planes, right, we get less objects, right? Which makes sense. So as we increase the number of planes that we check, we get less and less and less. I guess one of the planes don't matter, because by the time we hit 4, we sort of are we're sort of what we. Okay, so there comes a point where the planes don't really matter. If I do 1, I always got to make sure for shaders we have to compile them, right, into sphere V format, right? Right, we're at 138,000, right? So for 1 plane, and then if we don't check any planes at all, right, which it might crash, because I don't know if that's a valid. Is that a valid? We get everything, right? We get the whole. It's like we disabled the frustrum check. Okay, so you guys have a better understanding of what we are actually doing with with this application. All right, guys, I think this is a fair deal. We have covered a lot of stuff, so we understand now. If we do cull.comp, okay, so sphere V, guys, that's why I always have to compile the shader, because this application only sees the sphere V file, right? So we have our file here, but it has to go to sphere V, right? So this is called within the create pipeline call, okay? But anyway, guys, I think I've done enough. Guys, learn how to program your GPU. Learn how to program your GPU. Tutorial number 1 is for installing Vulkan on a Windows-based machine with a Vulkan-capable GPU. Install the Vulkan SDK. And then tutorial number 13 is installing all of these examples. Now, if you want to run the ray tracing stuff, I have a bunch of videos on ray tracing. You have to make sure that you have ray tracing capable GPU. For NVIDIA, it's RTX and above. For other vendors, Intel and AMD, I don't know what the deal is with those GPUs. But for NVIDIA, you need RTX and above. This application does not require ray tracing, so you don't have to worry about whether your GPU is ray tracing capable. It just has to be Vulkan capable. All right. This is CUDA Education. Thank you guys for watching. Have a great day. Tell your friends, like and subscribe. Guys, I need your help in making this a success. Making these videos, it takes time, it takes money, it takes effort. If you want to see these videos continue, support the channel, tell people about it. Work on this stuff in teams and groups, what have you. Use your time wisely. Learn computer graphics. AI can only create stuff that it's already been seen. With computer graphics, it's about creativity. Okay? So you could create something that you've visually seen in your mind, and this protects us from the AI onslaught. Okay? So definitely check it out. Support the channel. I have the tutorials. I will link the videos in the description below. Thank you guys for watching. Have a great day. Goodbye.